A car with mass of 1,200 kilogram and engine power of 62 kilowatt needs to climb an incline with a constant speed of 6 meters per second. The length of the incline is 100 meters, we see 100 meters, and its vertical height is 10 meters. The car experiences a frictional force of 820 newtons while moving up the incline. Ignore the rotational effects of the wheels of the car. 2.1. Write down the work energy theorem in words. So we go and state the work energy theorem in words, and that is the net work done on an object is equal to the change in the object's kinetic energy. Then we go to 2.2, and that says that draw a free body diagram of all forces acting on the car, and this one is 4 marks. So we see that this is the car. We can make a plan on the car. This car has got an engine that is pushing it forward. The engine exerts an applied force up plane, and then we were also told that a frictional force of 820 newtons acted on this car. So the frictional force is the force that is parallel to the plane, and it's exerted by the surface in the direction opposite to the motion. So the frictional force is going to be exerted downward the plane like this. So we have the applied force, upward frictional force, downward. Then the surface is inclined, so the normal force should be perpendicular to the surface. So the normal force should be in this direction, that's perpendicular to the plane. And then the gravitational force, which you can draw as a straight down force, or we can use the components to draw the perpendicular component and then the parallel component to the plane. So the answer to this question is this. We have the applied force, upward force, up plane. The frictional force is downward, and then the normal force is perpendicular. This the car has a dot, and then the gravitational force, we use the components method. The parallel component is in the same direction as the frictional force, and then the perpendicular component is in the opposite direction to the normal force. So that is the answer for this question. Then question number 2.3, we are asked to, if the engine of the car is 83% effective, that means if the power of the engine can develop power, but only 83% of it is working. That means the remaining 17% of the engine power or the engine force is wasted. Then determine whether it has enough power to get to the top of the incline, maintaining the constant speed of 6 meters per second. So here we have to determine whether it has enough power, which means we are going to calculate the power of the engine. Calculate the power of the engine while it is moving at this constant speed. And then we also look at the actual power of the engine based on the engine power and then the percentage that is effective. So what we do here is that we start by calculating the actual power of the engine. We are told that the engine is only 83% effective, which is 83% of the total power of the engine, which is 62,000 watts or 62 kilowatts, and that gives us 51,460 watts, which means this engine can actually provide a maximum power, effective power of 51,460 based on the information that we have about the power of the engine. The remaining 17% is what waste is used, is wasted. Then what we need to do is to find what is the power needed to get to the top of the incline. We need to calculate that based on the the forces involved in the motion. So yeah, when we check from the formula, that is the question, let's see the information that we have. We're given the constant speed of 6 meters per second. You see that determine whether it has enough power to get to the top of the incline while maintaining a constant speed of this. So when we check from the formula sheet, what do we see? We said that there are two ways to calculate power, which is power is equal to work done divided by time taken, and then power average is equal to the force, the forward force, or multiply by the average speed, which is also what, a constant speed. Now in this case we are going to choose this formula because we are given the average speed or the constant speed, and then what it means is that we need to find the average force, the forward force or the force applied by the engine, and then when we get this one and this, we can plug them into this formula, and then we get the power that the engine develops as it climbs the plane. So we say that our power is equal to the forward force, which is this force on the free body diagram, multiplied by what? The average speed or the constant speed that we're giving. And then we know that this was moving, the car was moving at a constant speed. Now that will help us to find the force F, because if the car is moving at a constant speed, it means that the net force acting on the car is equal to 0. Now let us remember that we are not going to consider perpendicular forces, because perpendicular forces are not doing any work. They are doing 0 work on the car. So we are not going to consider them. We will only consider the parallel forces, which is the applied force, the frictional force, and then the gravitational force parallel. So we say that our net force is equal to the forward force or the force of the engine minus the gravitational force parallel. Why do we say minus? Now these forces, the frictional force and then the gravitational force parallel, are doing negative work because they are acting in a direction that is opposite to the displacement of the object. So they are doing negative work. So we say, in other words, they are decreasing the speed of the object, or they are uh, taking, or they are removing energy from the system. While this one is increasing the speed, or it is increasing the energy of the system. So our net force F is equal to, now we expand, gravitational force parallel is equal to mg sine theta. This is the formula for Fg parallel, and we must remember this is not on the formula sheet, but it is something that we must always remember from our heads. Minus, now we don't expand the frictional force because we were given the frictional force. You can go back and check. The frictional force was given, that is a frictional force of 820 newtons. So once it is given, there's no need we look for it, so we just substitute for it. And then let's go back to the solution. So the net force is 0. Why? Because this object the car was moving at what? A constant speed. The car was moving at a constant speed. So the net force is 0. So we say 0 is equal to the forward force minus the mass of the car is 1,200 times the gravitational acceleration, which is 9.8, times sine theta. Now sine theta here is 10 over 100. Let us see why we say it is 10 over 100. Let's go back and check from the question. Now sine theta is not given, the angle is not given, but we have information to calculate the angle. Remember, sine of an angle is defined as what? The opposite, which is from here to here, which is the same as the height of the incline, divided by the hypotenuse, which is the length of the incline. And that is, we are going to say sine theta here is equal to 10 divided by 100, which is the length of the incline. So we substitute 10 over 100 as our sine theta, and then we continue. So when we do that, we get this, and then minus the frictional force, which we're given as 820 newtons. And then when we evaluate this with our calculators, we get the forward force to be 1996 newtons. Then we plug this value, which is the F, plus the constant speed that we're giving into the power formula that we have chosen, and then we get 1019, that is 1996 multiplied by the constant speed, which is 6. And then when we evaluate that, we are going to get 11,976 watt. Now, this is the power developed by the engine while climbing the incline or while moving up the incline. But the engine has a power of 51,460, and it needs only 11,976. That means it has more than enough energy to climb the incline. So the engine has enough power. It has more than needed. It only needs 11,976, but the engine has got what? 51,460. That's the engine, the engine of the car. So we conclude that it has enough power to reach the top of the incline. And that is how we solve this question.